The something else I'm going to talk about is what we see in lab number 8, specifically talking about impulse and momentum. Now, this is our chance to look at something completely new, or somewhat new, I should take it. In the beginning of the term, we started talking about motion, and we started by describing motion, describing properties of motion, describing how motion changes, using velocity and speed and acceleration and all of that. Then we brought in the idea of forces, and that gives us a new dimension, so to speak, namely that forces cause motion to change. Forces do not cause objects to move. Forces cause objects to change their motion. But one of the problems we run into in trying to unteach preconceived notions is this idea that if I put a force on something, there's going to be the remnant of that force to keep it moving. For example, the idea of what keeps the arrow flying. It was an old Aristotelian question. Aristotle asked the question, you put the arrow in the bow, you pull back on the bowstring, and you release it. The arrow leaves the bow and keeps going. Now, we know from Newton's laws of motion that the reason why the arrow keeps moving is because there's no force to cause the arrow to not move, to stop moving. But under Aristotle's idea, the bow imparted a property called impetus. And that property, so that arrow had impetus, and as it moved through the air, it used up the impetus to keep moving. In other words, it was kind of a residual memory of the force, if you will. Now, of course, the difference between Aristotle and Newton is Aristotle based his ideas off of pure logic and reason, which can lead you to some bad conclusions if you're not careful. And Newton based his off of observations. Namely, hey, if I don't see anything causing it to move, then why should it move, right? Or why should it change? So let's take a look at this idea about impulse and momentum. First off, the idea of momentum. Now, when you see momentum, it reminds me of the really, really bad physics joke, where the general was losing the battle and he needed reinforcements. So he sent a message to the sovereign king, his king. By the way, the name of the king was named King Tum, T-U-M, right? Okay. So the message, to make it really easy to remember, was only one word. Messenger arrived, he ran up to the king, and he just said, momentum. I told you it was a bad physics joke. Okay. However, I got a better question for you then, instead of what is momentum? Now we got a more interesting question here. So what is momentum? Yes? Don't you hate it when you knew what you were going to say when you put your hand up, and then once you get it called, you forgot what you were going to say? Happens to the best of us. Any ideas? What's momentum? Yes? Release of kinetic energy after a buildup of potential energy. Well, not quite, because first of all, we're not dealing with energy. We're not talking about energy. Energy is a totally different concept. So while there's a relationship between momentum and kinetic energy, that's not the reason what momentum is. Yes? How long an object keeps moving after you put a force onto it? Well, no. I mean, I understand where it's coming from, because that was kind of like off my definition of impetus. But impetus and momentum are two different things as well. Impetus is the memory of that force, which does not exist. And momentum is a different property. Okay, how about this? What does an object have to be doing or have in order to have momentum? it has to be moving. So whatever momentum is, and it's a very tough thing to define, and I understand why there's some difficulty with that. We're familiar with it because we've all experienced it, but it's like, what is matter? It's tough to define in an exact way. All we can say is that momentum is a property that an object has because it is moving. Is it an internal property? That is to say, is it a property that the object has? Or is it an external property? It's a property that the object is given or is imparted onto it. Okay, good debate there. Physicists, we look at momentum as a property that the object has. Now, it is subject to change. See, it's not, position is a property that an object has. And velocity is a property that an object has. But those are subject to change. You see where we're going here? Okay? Whereas mass or charge or volume, those are properties that the object has intrinsically. Okay, well, how is momentum related to motion? Well, let's go through a couple of questions and maybe we can kind of quantify it. Which has more momentum? A car that is traveling at 5 miles an hour or a bicycle that's traveling at 5 miles an hour? Why does the car have more momentum? More mass. Okay. Which one has more momentum? A car that is at rest or a bicycle traveling at 5 miles per hour? The bicycle. Why? It's moving. The car is not. Which one has more momentum? The car traveling at 5 miles an hour or the car traveling at 30 miles an hour? The car traveling at 30 miles an hour. Why? Because it's moving faster. Okay, so from our own experience and also as we've seen in lab number 8 when we start bringing this up, what we see here is there seems to be a relationship between the mass of the object and the speed of the object. Well, no, not the speed. We know, both from the experiments in lab number 8 and from our own particular experience, that momentum is proportional to the mass. The bigger the mass, the more momentum an object would have. Okay? We also see that momentum is going to be proportional to velocity, not speed. Which leads to a question for you. What's the difference between velocity and speed? What about direction? Okay, simpler way of putting it. There's of what? But what's the difference between the two? Yes? Velocity has direction, speed does not. See how easy that is? Because when I look at something and say that has a velocity, I'm not looking at trying to calculate it. I'm saying 45 meters per second to the east. That's a velocity. 30 meters per second, that's a speed. See the difference? Okay, so momentum is proportional to velocity. Again, we see this in lab number 8. Okay, therefore momentum is also a vector. I can have momentum to the left, I can have momentum to the right, I can have momentum up or down. Don't get caught up on the positive or negative stuff. Remember, positive and negative directions only exist on one dimension. If I say a football is being thrown in the air, what is its momentum? And you give me a positive something, I go, but in which direction? You've thrown a football in the air. It's moving in 2 directions, isn't it? Yes? Okay. So I often refer to, when I break it down into components, an X momentum, a Y momentum, a Z momentum. Those are the components of the momentum vector. Just like we would have the components of the velocity vector. Okay, so momentum is a vector quantity. It has direction. That means that if I have multiple momenta adding together, I could have a net momentum of 0. And if I have a net momentum of 0, what's the object doing? If it has a net momentum of 0, what's the velocity? 0, so therefore the object is not moving. Now, that does not mean that parts of the object are not moving. I'll give you a great example. Take a look at our solar system. From the frame of reference of the sun, we have all these different parts. Everything is moving around all over the place, right? Everything is moving, and yet when I add up all of those momenta together, the solar system itself is not moving. You see where we're going here? Huh? Kind of blew your mind a little bit? Okay, let's try another thing. Let me give you another example. This one's actually pretty straightforward. Let's say, for example, you have a firecracker at the end of a rope that's kind of hanging there. So there's the little fuse. Okay? What is the momentum of the firecracker as it's standing there with the fuse burning? 0. Then it goes boom, goes explode. Parts go everywhere, right? The moment after the explosion, when the parts first start flying around in all different directions, this part's going to have momentum going this way, this part's going to have momentum this way, and so on down the line. Part's going to have momentum all over the place. What is the net momentum? When I add up all of those parts, the net momentum is 0. Because everything is going to end up canceling out when I add up all of those momenta together. Now, that's not going to stay that way because once it explodes, then now gravity is going to pull things down, and now gravity is going to change the momentum of all of those parts. And in fact, we'll talk about that right now. So net momentum can be 0. Let's do something. So we can calculate the momentum. Momentum is not mass times velocity. Momentum is calculated by taking the mass of the object and multiplying it by its velocity. That's like saying force is not mass times acceleration. Force results in a mass accelerating. See the difference between the two? Hey guys, notice 2 things. Number 1, momentum is abbreviated with a P, not with an M. We don't want to get it mixed up with mass. And number 2, momentum and velocity are both vectors. That means we're going to have to write a vector equation, which means component equations, etc., etc. We still got to do all that stuff there. Okay? With me so far? Okay, good. Let's move on. Newton's second law. Let's take Newton's second law and rejigger it a bit. I'm channeling The Simpsons, right? Okay. Newton's second law. We are familiar with it in this form. A net force is going to cause a mass to accelerate. The acceleration is proportional to the net force and inversely proportional to the mass of the object. Okay? Notice how I can read that in the equation right there. Net force proportional to acceleration, inversely proportional to the mass. Okay, great, cool. All right, now we're going to do some changes here. Follow along with me. I'm going to take it, we're going to blaze a new trail. Okay? Oh, it's not that hard, I promise. My grandson, he's 13, taking Algebra 1 as an 8th grader. He can follow along with this. Okay? Let's start off with replacing the acceleration with the definition of acceleration. That means VF minus VI divided by delta t, or delta V over delta t. Okay? Then the next thing we're going to do is we're going to go ahead and expand the delta V. And that gives us m times the quantity of VF minus VI divided by delta t. Okay, wow, that's not too bad. You thought I was going to scare you with something really complicated, right? Well, hang on to your hats. We're going to do something complicated here. Yeah, we're going to use the distributive property and put the mass inside the group. And so we get m times VF minus m times VI. See how complicated that was? Yes, okay. Divided by delta t. I show that to Dr. Yang, and she would probably look at me going, why are you bothering? You can just go straight to it, right? Which, by the way, you really can. A little practice, and you don't have to worry. You can jump from one to the other. All we did was in the second line, we changed from acceleration to delta V over delta t. Everything else just follows from it, doesn't it? Except for one more detail. What is mass times velocity again? Mass times velocity is what? Momentum. So therefore, MVF is going to be what? Final in the momentum, PF. What is MVI going to give us? Initial momentum. So therefore, I can rewrite it to say that the net force is equal to PF minus PI divided by delta T. But since that's a difference, I can go ahead and replace that with a delta as well, and I come up with my final equation. F net equals delta P over delta T. Wow, that was tough, wasn't it? Yeah, okay. It wasn't too bad, no. But you see what we're doing here? First of all, it wasn't that hard of a progression, right? All we had to do was just replace the acceleration with the definition of acceleration, then kind of follow our nose. And we end up with that expression. Now, here's the key behind that. That particular expression right there, F net times delta equals delta P over delta T, that's Newton's second law. That is to say, a net force will cause momentum to change. Wow, that kind of, but now mind you, the change in momentum is going to take some time to do it, right? So visualize, if you will, there you are, your car's run out of gas, and there's a gas station nearby, so what do you got to do? You got to get out and start pushing, right? Or get some people, get out and start pushing. When you start pushing the car, you're going to apply a force to it. What's going to happen? Let's assume we don't have any resisting forces or very small resisting forces. What's going to happen once you start pushing on the car? Yes, but what's going to happen to the car? It'll start to speed up, right? It'll start to move. And as long as you keep pushing the car, what's going to happen to it? It's going to speed up as long as you continue pushing the car. When you stop pushing the car, then the speed will no longer speed up, will it? You following along? In other words, from this equation right here, F net is the force you're applying. Delta T is the time you're applying that force. The longer you apply the force, the bigger delta P is going to be, right? Because if F net remains constant as delta T gets bigger, delta P has to get bigger. Does that make sense? Okay, great. Oh, one more detail. What happens if I don't apply a force? What if F net is 0? Then what does the momentum do? It doesn't change. The delta P is 0. That means the change in momentum is 0. Not the momentum is 0. The change in momentum is 0. That means that if we do not apply a force, then whatever momentum the object has, that's the momentum the object keeps. You following along? That actually makes Newton's first law a little bit easier to understand, doesn't it? Okay, Newton's first law, we always thought of it that if you don't have an external force, an object won't change its velocity. Object in motion tends to keep in motion. An object at rest tends to stay at rest. That's what you've heard before, right? Well, now if we think of Newton's first law in terms of momentum, an object will keep its momentum unless acted upon by an external net force. So why does the bowling ball keep going down the alley? Because it has momentum and there's no forces to change its momentum. See where we're going here? Okay. And by the way, when Isaac Newton wrote his book about motion and stuff called Principia Mathematica, when he wrote it, he started off with his 3 laws of motion in the form of momentum. Okay? All right, so if the net force is 0, then there is no change in momentum. The momentum remains constant. All good, right? Let's see what we can do with that. I have a question for you. A tennis ball, which has a mass of 1/4 kilogram, is moving at 32.5 meters per second. What is its momentum? This should take you all of about 30 seconds to do. Okay? Everybody should do it. Don't wait for somebody else to give you the answer. What do you come up with? 8.13 is what I'm calling. 8.13 what? Excuse me? No, somebody has kilogram meters per second. Kilogram meters per second. That's my units of momentum. We don't have a special name for it. So unlike force, where we have the Newton, which is 1 kilogram meter per second squared, our unit of momentum is just mass times velocity, kilogram times meters per second. Okay? See where we're going here? So when I'm asking 8.13 what, now you know. Okay? No, we're not going to change it to momentums. Okay. No, we're not going to give it a special name because it turns out there's another relationship, and I'll show you that in a moment. Now here's another question for you. The ball, same condition, but now it's going to bounce off the wall and move at 22 meters per second. What is the change in the momentum? What is the change in momentum now? Okay, guys, what we got? No. No, not 88, not negative 2. Excuse me? It is not. It is not 2.63 kilogram meters per second squared. Any other ideas? Yes? Nope. Don't need the time. I'm asking for the change in momentum. That means, what do you need to know? You need to know the initial momentum, and you need to know the final momentum. And then you can find the change in momentum, right? Excuse me? Yes. Yes. Negative 13.6 kilogram meters per second. Now some of you are going, wait, what? How? Because y'all didn't draw a picture. I knew that. I knew it because it happens every time. Here's what I'm talking about. We draw the picture. Here's the ball going into the wall in the positive direction, and then here's the ball coming off the wall in the negative direction, which means, what's the final velocity, positive or negative? Negative. So that means that the final velocity, the final momentum, PF, is going to be equal to 0.25 kilograms multiplied by negative 22 meters per second. That gives you the final velocity, or final momentum, which in this case is going to be negative, 5 point something? 5.5? Yeah, 5.5. 5.5 kilogram meters per second. To find the change in momentum, it becomes minus 5.5 minus plus 8.13. And the answer is going to end up being in kilogram meters per second. Follow along now, guys? Have you seen this tennis ball problem before? Yeah, I think I've asked this tennis ball problem on every test. And on every test, you get it wrong because you don't take into account the change in the direction. You see what I mean? That's why I keep saying, draw a picture. Okay? Think I might want to throw another tennis ball problem at you again? Well, it may not necessarily be a tennis ball problem per se, but it may be a problem involving changing directions. That's always a one that I keep saying, velocity has direction, doesn't it? Okay, now let's go on a totally different path here. On a totally different path here, from Newton's second law, we start off with F net equals change in momentum divided by the time interval. Okay? Now, what you saw in lab number 8 is that when the cart ran into the force sensor, the cart changed its momentum, didn't it? The cart came in with a certain velocity, then bounced off with a certain velocity. Or it came in with a certain velocity and came to a stop, right? That force got applied over a period of time, so I'm going to rewrite that equation. All I do is multiply both sides by delta t. And I come up with F net times delta t equals delta p. The units on the right-hand side are kilogram meters per second. Since it's an equality, the units on the left side must have the same units, kilogram meters per second. Well, that kind of makes sense because we have newtons and multiplying it by seconds. Do a little dimensional analysis, you'll see those are the same units. So newtons times seconds is also a unit of momentum. Okay? But what am I trying to get at here? This particular equation, F net times delta t equals delta p. On the right-hand side of the equation is the change in momentum. On the left-hand side of the equation, we're going to call that impulse. Impulse is the force that you apply multiplied by the time you apply it. So let's go back to pushing that car again. If I want to get that car moving at a certain speed, then what I have to do is I need to start pushing with a certain amount of force. And the longer I can keep pushing with that force, the greater the change in the momentum is going to be. Does that make sense? Okay. There's a name for this particular equation. The name for this particular equation is called impulse momentum. It's called the impulse momentum theorem. You're going to hear me refer to it all the time. And you're going to see it referred to in the textbook and in the lab book. In the lab book, impulse is denoted with a capital J as a vector. Okay? I don't use it myself, I just use F times delta t. Okay, cool, fantastic. Now that tells us a lot of things there. F net delta t equals delta p. If I want to change the momentum in a certain way, then I have to have kind of a combination of things, namely force and time. Let's say, for example, baseball. The World Series is coming up, right? Braves versus the Astros. Okay? Please be aware that garbage cans are going to be prohibited in Turner Stadium. Yes? Okay, baseball fans know what I'm talking about. The rest of y'all, don't worry about it. I'll explain it later. But let's go on with this. Impulse, let's say you're playing a game of baseball, a game of softball. Got a runner on first base, no out. What's the play going to be for the batter? Yes, but if you got a runner on first base and nobody's out, baseball players, what's the play? Well, yeah, but we're going to play small ball here. Yeah, I know you got to hit the ball. You got to put the ball in play, but you got to play small ball here. You got two very close teams. Okay? Sacrifice bunt, right? Runner on first base, nobody out, you go sack bunt. Get the runner to scoring position. Now, in a sacrifice bunt, what you're trying to do is you're trying to drop the ball at the feet of the catcher. You want the catcher to make the play. Okay? So, let's think in terms of momentum. The ball is coming into the batter with a certain amount of momentum delivered by the pitcher, right? We want the momentum of the ball to drop to zero. We want to change the momentum to zero. We want to make the smallest change in momentum possible in order to get the ball to drop to zero. So when you hit the ball with the bat, when you're bunting, let's take a look at these two terms, F net and delta t. What do you do as far as the force is concerned? Yeah, but you're applying a force. What are you going to do with that force? How much force are you going to apply? How much force are you going to apply to the ball? You're going to bunt the ball. Okay, you're not thinking in terms of, do we have any baseball players in here? Do we have any softball players in here? Anybody ever lay down a bunt? Okay, but you've had an idea, but you got an idea. If you played in 7th grade, you should have gotten at least a little lesson on how to do a bunt, right? So when you hit the ball, how much force are you going to hit the ball with? Very little force. Guys, we're talking practicalities here. We're not talking physics. We're talking practicalities here, applied physics. In other words, you don't want to hit the ball hard. You want to hit the ball just hard enough to stop it from moving. You see where I'm going here? Okay, that's the first thing. So F net is going to be as small as possible. What about delta t? What about the time interval? What do you want to do? You want to keep in contact with the ball or what? As long as possible? As little contact as possible. That means when the ball comes in and you hit the ball, when you bunt the ball, you hit the ball, you bring the bat back. You don't go into the ball, you bring the bat back. Okay? Why? Because you want to make F net as small as possible and delta t as small as possible. By doing that, you're going to get the absolute minimum change in momentum. Whatever momentum the object had coming in to 0. We want that to be a negative change in momentum. You see where we're going here? Now, let's change it. Bases loaded, 2 outs. You're losing by 3 runs. Okay, so what are you going to do? You got to go for the home run, don't you? Yeah, you want that grand slam. You want the glory. You want that walk-off grand slam so they can write about you in the history books and all. Okay? So what are you going to do with F net? What are you going to do with that force? As big as possible. That's the reason why you go to the weight room. And that's the reason why you work on your technique. You want as big as possible. Arms, hips, everything, right? F net as big as possible. What about delta t? You want it as big as possible because F net times delta t gives us the change in momentum. If I'm going to go over the fences, I've got to get the biggest change in momentum possible onto that baseball. How can I keep a long contact with the ball to keep imparting that force? Follow through. Follow through. Just keep the swing through. Don't be like the little leaguer. Once you make contact with the ball, stop swinging. You keep swinging all the way through so that the bat ends up behind you. If you play golf, you know what I'm talking about. Follow through all the way through. Okay? Okay. Why? If you want the smallest possible change of momentum, then we want a small f and a small delta t. If you want the biggest possible change of momentum, if you want the biggest possible delta p, then you want the biggest force over the longest period of time. But what if you're not interested in the force per se? What if you're not interested in the change in momentum per se, but more interested in the force? There you are driving along in your car. You're going 60 miles an hour driving in your car, and you want to come to a stop. That means your change in momentum is going to be the mass of your car multiplied by the 60 miles an hour in the negative direction because you're coming to a stop, right? Now, there's one way you can come to a stop, of course. You can apply the brakes. If you apply the brakes, you're going to apply, let's say, again, I'm making up these numbers along the way, so this is not the actual numbers. But say you apply 500 newtons of force to come to a stop. How long does it take to come to a stop when you're driving at 60 miles an hour? A reasonable amount of time. Okay, remind me not to drive behind either of you. let me translate. 5, 7 seconds, I can understand that. That's if you slam on the brakes. But what if you're coming off that off-ramp? It's going to take a certain amount, it's going to take a longer period of time if you're coming on the off-ramp, right? 60 miles an hour to 0 in 10 seconds. Shoot, Porsches do 0 to 60 miles an hour in 10 seconds. Now, your brakes can certainly do that, but what I'm trying to get at is let's say it takes, for example, 20 seconds. Does that sound reasonable? 20 seconds to come to a stop if you're going from freeway speeds? Yeah? Okay. So that would mean that the change in momentum would be the 500 pounds multiplied by the 20 seconds or whatever that turns out to be. Okay? Now, let's take the same scenario. Well, a similar scenario. You're driving at 60 miles an hour, and the tree jumps out in front of you. You're going to come to a stop. Okay? But it's not going to take 20 seconds. That's right. You're going to come to a stop, but it's not going to take 20 seconds. What's going to end up happening is it's going to take like 0.2 of a second. That means it's going to take 1/100th the amount of time. So what happens to the force that the tree is imparting on the car to bring it to a stop? 100 times bigger. So it was 500 pounds, now becomes 50,000 pounds of force. Okay, why am I saying this? Because if we want to have the same change in momentum, but we don't want to die doing it, we need to decrease the force, don't we? We need to make the force small, at least survivable. How do we make the force small to come to the same change in momentum? Airbags. Increase the time. Airbags is exactly right. Because what airbags do, okay, follow along the story if you will. You're driving along in your car, the tree jumps out in front of the car. The car comes to a stop. It's going to take a certain amount of time to come to a stop. But we don't care about the time the car takes to come to a stop. We care about the time it takes for you to come to a stop. Right? Because that's going to relate to the force imparted on you to bring you to a stop. Now, if you are driving a 67 Challenger, you are going to come to a stop in a very, very short period of time because that car will not dent. It'll run in and it'll stop. It won't collapse. It won't dent. This is the old land yachts, right? Okay, they were made to survive. The cars back in the 50s and the 60s were designed to come through crashes intact. The problem was the people inside didn't. Okay? Because it took a very, very small amount of time to bring the car to a stop. And so Volvo and BMW and other European manufacturers instituted the idea of the crumple zone. When the car runs into the tree, the front end collapses. As the front end collapses, what happens to the time it takes to come to a stop? It increases. That decreases the amount of force required to bring you to a stop. There's an old saying that the CEO of BMW or Volvo, I can't remember which one, I got to look it up on the internet sometime, but he said that we will destroy the car so that the customer will buy a new one. Which makes perfect sense, right? It's like, wow, I had an epic crash. I'm alive. I'll go get another one of those. You know, that's a selling point, isn't it? Okay, so that's the first thing. The crumple zones, the invention of the crumple zones. The second thing, you want to come to a stop with the vehicle. You don't want the vehicle to bring you to a stop. What I mean to say is if you're wearing your seatbelt, when the car starts crumpling and starts to slow down, you will slow down with the car. If you do not have the seatbelt on, then while the car is slowing down, you don't. And something will have to impart a force onto you to bring you to a stop. The steering column, the dashboard, the windshield, maybe the tree because the windshield didn't work. Are you following along here? So you wear the seat belts. But there's one other little invention that came up in the 70s, namely the airbag. And when you run into the airbag, when the airbag inflates, it inflates very, very quickly. The airbag needs to be fully inflated before you run into it. Why? Because you've seen the stunt movie back scenes where guys take these big drops and they fall into airbags. What do those airbags do when the stuntman falls into the bag? They collapse, don't they? Because it extends the period of time to bring the stuntman to a stop. If the airbag didn't collapse, it'd take a very short period of time. That's like doing a belly flop into the water, right? Okay, so the airbag needs to be fully inflated before you hit it. And then when you hit it, it deflates, increasing the amount of time it takes to come to a stop, and therefore you are able to survive that particular kind of crash. Following along, guys? So the whole thing is based on this particular equation, F net delta T equals delta P. You can either stop from 60 miles an hour to 0 in 0.2 of a second, or you can stop from 60 miles an hour to 0 in about 1.5 seconds. One is more survivable than the other. Okay? So, question, go ahead.
Does the J equals force?
No, the J in that equation, J equals F times delta T, represents impulse. Okay? The J there is the variable symbol. Okay? And the units of the impulse are going to be the same as the units of the momentum, because impulse is equal to the change in momentum. Now, all we need to do now is to find out what the average force that the wall exerts on the tennis ball is. Just take the change in momentum, that negative 13.6 kilogram meters per second, multiply that by the time interval being 25 thousandths of a second, and we end up getting, that's the wrong answer there. Okay. Well, oh, no, I'm sorry. If we take the change in momentum and divide it by the time interval. So the change in momentum was 13.6, and we divide that by 0.025 seconds, and we end up getting the wrong number, the wrong answer. No, I can't. Let's try it again. What was our change in momentum in the problem? Negative 13.6 kilogram meters per second. Okay, and our equation is F delta T is equal to delta P. So that means we need to take that and divide it by 0.025 seconds. So 13.6 divided by 0.025 seconds. There we go. There's the right answer. 540. 540 newtons of force. Fairly significant, yes? Okay. I got a couple of interesting questions for you, and then we'll wrap it up. A golf ball is resting on a tee when it's hit by a club. If the ball has a mass of 0.05 kilograms and has a final speed of 44 meters per second, what is the impulse on the ball? Okay? What's the impulse on the ball? So what's the impulse? No. What is the impulse on the ball? So what is it? There are a number of reasons why I would say an answer is incorrect. How do we find impulse? Okay, what's another way of finding impulse? Change in momentum. Which one are you going to use in this particular case? So what's the change in momentum? Excuse me? Okay, the units, 2.2 kilogram meters per second. If you don't give me units, you are incorrect. You following along, guys? I keep stressing that. You saw that in the last test. Now that you know what the impulse is, what is the net force acting on the ball? Oh, that gets a little bit more interesting here. How do I find the net force? Well, from our impulse momentum theorem, F net times delta T is going to be equal to delta P. Okay? That means in order to find F net, we need to find out delta T, don't we? Correct? Well, let's assume that the ball has a constant acceleration. If we're using the average force, then we'd have a constant acceleration. Then we would know, let's see, we know delta x, which is 2 centimeters. We know the initial velocity, which is 0. We know the final velocity, which is 44 meters per second. So therefore, we can find delta t. Do you see? And once you apply that, you can then, once you find delta t, you can now go ahead and solve for F net. So as you can see, the stuff we've learned in previous sections, that still does come back to you again and again and again. Okay? I'll leave that as an exercise for you all to work on. You should be able to figure it out. It should be a really, 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 really big force. Okay? Because if anybody's ever seen a slow-mo video of a golf ball being hit off of a tee, ball traveling one diameter to get up to speed, that's a squish, to say the least, yes? Okay. Any questions for me? Any answers? We're not giving any tests right now, so we're not going to have appeals to higher authority. By the way, speaking of tests, if you look on the calendar, I've got the schedule, I've got test number 3 on the calendar there. Now remember, test number 3 is the day before Thanksgiving, and I've got the first week in December on the calendar now too. So, wow, congratulations. This week is going by very, very fast. Okay, if you got questions on the homework or anything like that, I will be in the classroom this afternoon. I'm planning on being in the classroom tomorrow evening after 7. Please do me a favor and don't wait until then to start your homework. Get your homework started now so you have some reasonable questions. On that note, I will see you guys later.